Alrighty, so let me turn this on and we'll get going just a little bit late, sorry about that. Okay, so today we're finally ready to start looking at trajectory planning, and in order to plan our trajectories, as I've already mentioned, we're going to use linear interpolation. You'll see that linear interpolation is very, very easy to implement. Really the only thing that you have to do in order to implement this final program is clean up your CCD algorithm a bit, and probably package it in the form of a function. When I wrote my solution, which I'll show you guys here in a few minutes, that's exactly what I did. I just took my crappy code out of problem 4, cleaned it up, put it in the form of a function, and then called that function anytime I needed to go in and calculate a set of DH parameters. Okay. So as our warm-up, we're going to go through and determine the minimum holding torque requirements for each of these joints, and just so that we remember, how do we do this?
We just find the determinant.
Okay,
Essentially.
we know that it's the cross product. Let me scroll down here just a little bit. We know that the torque is defined as the cross product. So the torque is the cross product of the position vector and the force that we're assigning to it or attaching to it. How are we going to configure this manipulator in order to for us to be able to interpret it, specifically so that we can determine these minimum holding torque requirements. How are we going to orientate the manipulator? We're going to have it,
Everything straight.
yeah, we're going to have everything oriented horizontally.
So that we can do our force.
Exactly. So what we're going to do is we're going to have this manipulator oriented horizontally, and that's not quite right. It should be more like out there. So this is going to be oriented horizontally, meaning that theta 1, which, yeah, theta 1 is going to be holding all of this, or it's going to have a holding torque to support the entire arm. Theta 2 is going to have a holding torque to support this portion of the load, and theta 3 is going to have a holding torque to support that portion of the load. Okay. So here is our theta 1, theta 2, theta 3. This then is our 4 meters. This is our 2.5 meters. And finally, this is 1 meter. You'll notice in the notes that I put this at 40, 25, and 10. And that didn't seem very realistic to me, so I changed it to 4. That's still 16 feet, so that's pretty honking. But there are some really sizable industrial robots out there. If any of you have ever worked in a manufacturing environment, you have probably seen very large robots in those manufacturing environments. In fact, the Hitachi robots that were responsible for the material handling at Excite Battery back in Kansas probably had an initial joint length of something close to 16 feet. So that's not unrealistic. Okay, so in this case, how are we going to go through and find the holding torque necessary for theta 1? And by the way, what force is associated with a 25 kilogram mass? And I shouldn't say force, what should I be saying? Weight, right? Because this is going to represent a mass that's being attracted through gravity, okay? so we're going to have a 25 kilogram mass, which represents, let's see, weight of mass times gravitational constant. So what is the weight of that mass?
$245.
245, it's going to be the 25 kilograms times the 9.8 meters per second squared to give us 245 kilogram meters per second squared, which is our Newton. Now, what's our force vector going to look like then? This force vector is going to, let's see, if we say this is x, y, and z, there's no x component, no y component, and only a z component. Therefore, the force vector is going to look something like this. 0 x component, 0 y component, and then a negative 245 z component, meaning it's being attracted towards the planet. Okay. Okay. Well then, if we've got the force vector, and note that that's the same force vector that we're going to be using for each of the torques, okay? Well, how are we going to determine the position vector for each of our joints? That position vector is going to be nothing more than the length out to that point, right? So in this case, if we're hopefully laying this out so it's easy to calculate, we'll recognize that if we set this on the x-axis, then we have an x displacement of 4 plus 2.5 plus 1, so that's 7.5 meters, okay? So our R1, the position vector for theta 1 to the end effector would just be 7.5, 0, and 0. Of course, we don't have to orient it this way. We could align it anywhere on the xy plane. But the nice thing about doing it along a specific axis is then we don't have to consider these other components. Good? So, with that being said then, our torque for first joint is going to equal, let's see, the cross product of the position vector and the force vector. So I'm going to go through and write this in determinant form. So I, J, and K. Let's see, our position vector R is 7.5 for our x component, 0 and 0. And then finally our our force vector is 0, 0, negative 245. And do we end up with any I component? No, because in this case we see that we have a 0 minus a 0, so there's no I component. Is there a j component? Yeah, there is. So it's negative j times 7.5 times a negative 245. So there is a, let's see, 0i minus a negative, so plus a j. And what is 7.5 times 245?
1837.5.
1837. And is there a k component?
No.
No, because there's 0 and 0, so there's no k component as well. And remember yesterday, I said specifically when we do this, it's really nice to align it along an axis, because what are we primarily interested in here? Not necessarily the torque vector, but the magnitude of the torque. That's what our motors are rated in, okay? So in this case, if we wanted to determine the minimum holding characteristics, holding torque characteristics, we're just going to determine the magnitude. Well, since the I component is 0, the K component is 0, the only component that has any magnitude associated with it is J, therefore we can say that the holding torque, or the magnitude of the holding torque is 1837.5 Newton meters. That makes sense? This entire time that atlas has been right there in your way, hasn't it? Wow, that's awesome. And you haven't said a word. I'll set it over here in front of Amber. Which is what I thought initially, and then I realized that would have been kind of rude. Okay. How can we go through and do the exact same thing for theta 2?
Just not have the 4 meters onto it.
Yeah, we just knock off the 4 meters. In this case, we're going to have a displacement or a x component of 3.5 meters. Is it necessary, if we use this approach, to go through and find the dot product every time? No, in this case, we can just say that, well, each time we do this, we're always going to end up with a j component equal to force times distance, okay? So if we do this, we can say that, or if we set this up along one of our axes, we can say that the magnitude of the torque on the second joint is just going to be the force times distance, the 245 newtons times the 3.5 meters. And what's that give us?
857.5.
857.5. Okay, and finally, I'll do the last one. Magnitude of the torque on the third joint would be the 245 newtons times the 1 meter to give us 245 Newton meters. So what would, these are the minimum holding torques that we need. What would the motor specifications, what would we look for in the motor specifications if we were going out to purchase some motors to build this robot?
Probably a 20 or 25 tolerance.
Yeah, probably we'd go over this by a minimum of 25%. It just depends on how robust we want the system to be. If we're selling it to a consumer market, well, consumers are just going to go out and buy a replacement if it dies. So we might just run it with these baseline specifications. Industrial producer, we'd go with a minimum 25% safety factor. Medical instrumentation and stuff, we'd probably have to shoot this up over 50 or even 75% because anytime you're working within the medical industry, you're going to have extremely high factors built in to verify repeatability and safe operation of the equipment. So, good. Okay, so the reason I introduced this is just to give you an idea how you can start rating your different components when you start approaching your senior design. And when you get into engineering, if you secure a truly engineering role, you're going to be looking at speccing out devices and components and everything else. And it's really good to maybe not necessarily be able to spec out a stepper motor, but to have some experience speccing out something. So, good. Does this mean that this manipulator is ever going to have to hold something in this particular configuration? No, it may never actually achieve this particular set of joint parameters. But just to ensure that there is no slipping that occurs, these would be the minimums that we'd select. Okay? Any questions there? When you guys get your senior project, if you do anything with stepper motors, or anything like that, just stop back by and I'll walk back through, you know, the step sequence and, how you can interface it to your microprocessors or to your project or whatever else. They're really not hard to work with. They are just very mysterious if you've never worked with them before, okay? It's really interesting to have something sing at you when, you know, you're sending the wrong pulse train to it, and it's just not doing what it's supposed to be doing, so. Okay, so with that then, we will get to this idea of linear interpolation. So I first ran into linear interpolation, of all places, in a hydrogeology class that I took. It turns out that when you're looking at groundwater movement, let me draw this, what you tend to do is, let's say on a 1 acre by 1 acre plot, you'll go through and drill a number of wells. Okay, so those wells then are intended to sit there and monitor the groundwater level and the flow rate that's present within that aquifer. Okay. Well, if we know the groundwater level and flow rate at any one of these wells, what can we probably do at any point between these wells? Can we determine exactly what's going on? No, but we can probably approximate those, the movement within these points. For example, if we have a flow rate in this direction and a water level of, say, negative 50 feet here, and we have a flow rate that's kind of in this direction and a elevation of negative 75 feet, what are we probably going to suspect is going on here? From these 2 points, it's kind of hard to say. But if we were to go through and start guessing, somewhere between this point and this point, the direction of flow is probably going to do something like that, and it's going to increase its head. It's going to increase in elevation. So I obviously drew this backwards, didn't I? Because we don't run from lower elevation to higher elevation. Okay, more than likely then the direction would be something like that, and we could go through and draw a slope field if we had enough of these points in place. This seems kind of an abstract example, but how can we think of, or how can we apply the same idea to the motion of a robot? This last week, we did a couple things. We had a robot with an end effector at some initial location, and we had a destination, and the second part of the assignment was to get that robot from the initial position to the destination. And we saw that as we did this, that end effector just kind of did one of those things, right? It didn't follow any kind of prepared path. What's the ideal case?
Straight line.
Straight line, shortest distance, right? So what we're going to do is figure out a way to make that end effector follow a straight line. We don't care what the joints do as long as the end effector is following a straight line, okay? So we're going to go through and interpolate a series of points between this point and this point. That means that we're going to take and essentially create an equation of line between the 2 points and follow that line as we move from one point to the next, okay? What's the easiest way we can possibly do this? And I'm going to exaggerate this a bit more. So we have our initial position here, and we have our destination. And let's say that we want to take 200 steps between the initial position and destination, just because I'm kind of stuck on 200 for some reason. It's what we used last week for our motion, it's what we'll use this week for our linear interpolation algorithm.
Can we just take the total distance and divide it by 200?
Yeah, absolutely. We can take the total distance and divide it by 200, right? That means that if we take the total distance here, divide by 200, we're going to move 1/200th of that distance, then 2/200ths of that distance, 3/200ths of distance, right on down. Now, that's totally approachable, it's totally doable, but there's a much easier way to interpolate, particularly within MATLAB, this field. Do we have to worry about the distance at all? Within the CCD algorithm we do, but that's already part of your CCD algorithm. We don't need to change that, okay? What would be a really easy way to interpolate these points without having to do a bunch of really fancy calculations? Do we have to look at X and Y combined, or can we segregate X and Y?
Can break them apart.
Yeah, we can absolutely break them apart, right? We can go through and say that the X displacement is going to be broken up into 200 steps. The Y displacement is going to be broken up into 200 steps. And guess what? When you have this Y step value and this X step value, if you go and say move 50 Y steps and 50 X steps, what's going to happen? There's going to be 50 steps into that line, okay? So this works out really nice because suddenly we don't need to worry ourselves a whole lot about having really complicated equations here. We can come up with an equation for this Y step and for this X step, and we got it done. In fact, it's going to look very similar to the for loop that we used this last week in order to move our joints. Except for in this case, we're not going to be iterating through our joint steps, we're going to be iterating through our end effector destinations, okay? So with this then, let's go ahead and take a look at how we can implement this in MATLAB. And I already had one open, so this will be interesting. Okay, so just as an example, what I'm going to do here is open up the one that's already script. Okay, so I'm just going to go in and I'm going to set up my axis like I have done in the past. Notice that in this particular approach, it doesn't matter if we're working in 2 dimensions or 3 dimensions, okay? If we were to go through and try to come up with an equation of the line in 3 dimensions, it'd be a little more complicated because then we'd have to consider the slope along the XY plane, the slope along the XZ plane, and then slope along the YZ plane. We don't need to do that using this approach because if we extended this into 3 dimensions, then we just have to break it up into the X step, Y step, and Z step, okay? We're not going to do that this week. We're going to continue working with our planar robot. But if you needed to, it would be easily done, okay? So I'm going to start off by setting up my, and let me do the magnifier thing here. Okay, so So I'm going to start off by setting up my axis. I'm going to clear the axis. I'm going to tell it to hold the plot area on. Turn the grid on just for the heck of it, because I do this every time and I tend to be kind of boring that way. Now I'm going to define our axis as, I don't know, what do you want? Maybe -50 to +50, -50 to +50. That seems like a big enough area. We will in fact be using the same manipulator configuration we did last week. It's going to be the exact same set of DH parameters. All you're going to be doing is implementing it with a different trajectory planner in place. So everything from last week is going to come right on over to this week, with the exception that you're actually going to make your manipulator follow a straight line. Okay, I'm sorry, you're going to make your end effector follow a straight line. Okay. So after we do this, I'm going to go and just select an input to represent my initial position, and input to represent my destination. So I'm just going to go through and say that X init, Y init is equal to, see if I can spell it right, G input 1. On this, when I was working on this in my office, what I did was I tried to have 2 mouse clicks, okay? And you can do that if you feed it into a 2x2 array. Sure enough, you can just tell it I'm going to collect 2 mouse clicks, store those in an array, and use them, okay? But for some reason in my, close-minded boneheadedness, I couldn't get the mouse click coordinates out of that matrix. So I'm just going to do it the really low-tech way and save myself a lot of headache and confusion. So, okay, after I do this, I'm going to, I'm going to go in and plot it real quick. So the way I plotted this in class was I did something like X init for both my initial and terminating X coordinate, Y init for both my initial and terminating Y coordinate. And then I'm going to use red as my color and a plus sign for my marker. Okay. After I do that, I'm going to do the exact same thing with my X and Y dest. I'm going to just enter in my X destination and Y destination using a mouse click. And this is, again, just the setup. I wanted to kind of go through and build this so you guys could see me fumble around with my typos after I get ready to run this. So, okay, plot that point. And I'm going to see if it works here in just a second before I get too much further. So X, this. Okay, so run this, whatever, okay, fine. Click there, oh, I messed something up, so where did I mess up there? I must have something spelled wrong. I suppose I did. Line 7, so do you see a typo in there?
Isn't that G in it, or is that okay? Same line you were just on.
Says it's in line 7 here somewhere. get rid of that for a second and see if that. Okay, so it was that, I'm not quite sure why that would be. Let's do something like this. Because I'm pretty sure that works. No? No. Oh well, we'll just, I'll look up the parameters for the, I suppose I can see how I formatted them previously. Summer, here, here. Oh,
R plus.
Okay. Jeez. So it is the color, then the symbol, close. There are a few different formatting rules that don't seem to be quite consistent with MATLAB, if you haven't noticed. So there's that one, and where's the problem in the second? Says G input. And now we should have this portion working. I don't know if you guys have gotten into the habit of it or not, but I always baby step my programming. I get little pieces working, that way I can move forward. Okay. So now that I have my inputs going, what I can do is I can set up a for loop. And this for loop is going to do exactly like I said. It's just going to figure out what the Y step and the X step is, plot a point corresponding with that, so that I know what the destination that I want the CCD algorithm to calculate the set of joint parameters for is. And I know that it's a horribly run on seconds, but that's fine because in most instances I don't use words. At home I don't talk, so. And my wife is probably the one that wants me to talk the most, so. Okay, so what I'm going to do is just say that the X coordinate that I'm going to be plotting is going to be the current step position on my line. So I'm going to say it's the nth step in, and how am I going to figure out what the step value is, this X step. That X step is just going to be the destination minus the initial point divided by number of steps, 200. So it's going to be, let's see, the destination, so X dest minus X init divided by the number of steps, 200. And are we done? If we leave it at this, where is the first point going to be placed? Well, it's starting with a index of 1. It's going to be placed really close to 0. It's not going to be right at 0, but it'll be really close to 0, right? Okay. Where do we actually want it to start? Well, we want it to start at the initial X position. So we're going to offset it by the X init location. So it'll be plus X init. And now we have the X coordinate calculated. All we're doing is coming up with a linear equation for that X coordinate. And what this is going to do is on the first loop through, it's going to calculate that location. Second loop through is going to calculate that location, and subsequently through. Okay, the Y equation is going to be almost identical. It's going to be n times the Y dest minus Y init divided by the number of steps we're using plus Y init. And now we have an interpolated point along this interval. Now, how many of you have heard of extrapolation? Could we apply this to an extrapolated point as well? Not that we want to in this case. Absolutely, right? Because all we do then is move outside of the interior of this line. So when we're extrapolating, what we're doing is we're providing a linear representation on the interior, but extrapolating it to the exterior region. And extrapolation is oftentimes used when your data set is limited. When you are on one of the two boundaries of the extent of your data set and you want to see or predict what the behavior is when you move outside that data set. So, okay, so with that being said then, even though we know what extrapolation is, we're going to always be interpolating. Okay, so with this being said then, now I'm just going to plot these points. So I'm going to plot the x's as the beginning and end, the y's as the beginning of end, and that's just going to demonstrate that we're getting the job done. So,
Can you put commas in between them, the x's and y's and stuff, or does the spaces work too?
Say again.
The commas between
Yeah,
the x's and y's.
when you're defining vectors like this, you can either separate the elements of that vector with a space or with a comma.
Okay.
Typically what I do is if it involves an equation, I put a comma in there just to make sure I remind myself where it starts and stops. But otherwise I get kind of lazy and just leave a space in there. So, okay, and then I'm going to do green and the plus sign now, and so when we run this, unless I have something messed up, we have the interpolated points between the initial point and the destination. It's green. And so how are we going to take this and use it with our CCD algorithm?
We're just gonna put that end effector on the line and like slide everything else.
That's exactly it. What we're going to do is we're going to say, okay, well, we need to calculate the initial set of joint parameters, okay? Then we're going to go through, increment our end effector location, find the new set of joint parameters, increment the end effector location, find the new set of joint parameters all the way down, okay? Now, like I said, this is not a big step beyond where you were last week with your program, okay? We are not going to be drawing the paths like we did last week because that's not part of this assignment. We want to make sure that we're producing as efficient of a piece of code as possible, and that's just not necessary. But on the same hand, if you have your CCD algorithm working, then this is not terribly difficult to build up and get going. In fact, I had to, so this morning about 9 o'clock I started it. I fumbled around with it and got something that was erroring out like mad at 10, at which point I went and got coffee. On the way down there, I was like, oh, I know the problem. When I got back, about 15 minutes later, I had my code running, okay? So this should be a fairly simple program to implement. Okay, do you guys want to see my solution then?
Sure. Why not?
Let me- Okay, so I will run it here at the path. Okay, so exactly the same as what we had before. We have the initial parameter that's randomly generated. We select a destination, and then we go through and draw the linear path as we're moving towards the destination. And notice that I left the initial configuration on the screen just so that I could remember where we started at. Cool. Notice again that I have not restricted any joint motions. Now, I think in a 10-week section, I probably would include that as part of this assignment, just making sure that we did not cross over any of the segments as we do in this case. But in a summer session, since we only have, a week and a day left of class, I'm not going to make that a requirement of the program. So run it again real quick. Now you'll notice, as is the case with the CCD algorithm OVAS, when you come up with a solution that's near the perimeter of your workspace, you're going to have a problem as you're getting closer and closer to that boundary region. So as we get closer and closer up there, you notice that it's slowing down. And that's because it's having to make more and more corrections in order to perform that CCD algorithm. Each time it's moving towards that point, it's actually having to adjust the base joint here, which means that it's having to go through and redo all of the calculations at least once. Cool. Okay. Now there is something that's really kind of a problem with this approach, and let me see if I can't. Okay, so we'll go through and move this guy. I don't think I'm going to have a problem. I tried to use the CLA, and that worked great, but it would not go through and actually plot the line. So that's the reason why you see this white region here is because we're actually clearing the previous line and drawing a new line each time. So
that's all you have is a CLA command in front of your plot.
that's the original way I tried to implement it. What I did in this case was I redrew the previous configuration in white before I drew the new configuration. So it's kind of cheesy, but you know, it gets the job done. So I will try to reproduce the error that I speak of. So maybe this will get it done. Nope, it's not going to do it today, or this time either. Okay, there's one of the instances where it's approaching that boundary region, so it's really having to spend some time calculating the next solution for that interpolated point. Okay, what happens on occasion, particularly when you have a joint that crosses over another joint, so let me sketch it here while this thing is sitting here thinking about meaning of life and stuff, is let's say that we've got a situation where we have the second and third segments right on top of each other. So it might look something like that. What you'll see as it's moving through is a sudden erratic behavior. So it might do something like that. So in the initial, and I know I'm only drawing in 4 joints. Okay. In the nth step, it might look something like that, and for some reason I didn't bring one of my multitudes of colors. And the n-1 step, or n+1 step, it might look something like that. Meaning that this joint angle has unrealistically changed with that next solution that is solved for the n+1 location. Okay. the reason for that is because it's going through and recalculating all of those joint parameters, not just the joint nearest the end. So if it, ideally, if the end effector is moving on this line, the minimum number of adjustments you would have to make is your last joint and the n-1 joint, okay? But in the situation where that's just not, or maybe you adjust it and it doesn't produce the shortest distance, then it's going to change the rotation that it searches for the destination on. And in that case, you're going to end up with a discontinuity in those joint motions. Do you guys kind of understand what I'm meaning there? I'll try to, I'll break out of this since it's obviously, you know, really having a hard time contemplating why it exists. Okay, so close this. Run it again. Okay, maybe if I do this, lodge it here, and still smooth. There we go. So there was one of those discontinuities where the motion that is simulated would not represent the physical motion just because of that discontinuity. Good? So what do you think of this final assignment? Like I said, the strategy I would use is to try to take your code that you have, clean it up as much as you can, and then create a number of functions out of it. Because if you go through and implement this as just one big script, what you're going to end up having is kind of a mess in your code. So I was able to cut my code down to, well, my code length is now about a third of what it was for the previous thing, because now I have a function that goes out and draws my joint parameter, my joint configuration, and a function that calculates the CCD algorithm and so on and so forth. So now each of those are a function, therefore I no longer need to type in or copy and paste big long sections of code when I need it. I can just call that appropriate function. Good? Okay, so with that then, I will stop talking. We will then come in tomorrow. I will have the last programming assignment posted. Later on today, we'll come in tomorrow and start working with it. And I'm thinking right now that it'll have two parts. It'll have this as the first part, and then the second part will require you to enter in 3 destination points. And so if you enter in 3 points, you would start here, you would move to here, and then you'd have to plot the trajectory to the next point, perform the motion, then to the next point, plan the motion, and so on and so forth. So that would be nothing more than, you know, a way to fill up the screen with a bunch of squiggly lines. So, but it would give you a chance to, you know, do something a little more involved than just plan a single path. Keep in mind too that when you see that second part, I'm not going to expect you to round the corners as I was discussing yesterday. You're going to actually achieve the end point and move to the subsequent point and so on and so forth. So, you're thinking about something, I can.
No, I was going to ask you if you figured out a better way of passing all the frame locations between your functions, because I had a massive, it was just like one matrix that had all the information.
Yeah, and that's, I just passed the parameter matrix back and forth. I mean, if you think about it, it's really not that bad because it's only, let's see, they're doubles. There's 18 elements in it. So each double is 4 bytes. Is it 4 bytes or 8 bytes? It's 64 bits, so it'd be 8 bytes. So if we have 24 times 16, I'm not even going to try to do, it's 768 bytes that we're passing back and forth. And given that we're working on a 2.4 gigahertz machine, it's.
Well, I just didn't like having to like, whenever it went into a function, you had to pull each frame out and be like, okay, frame F is.
Well, see, the thing is your CCD algorithm only requires you to calculate the last frame. Because everything in your CCD algorithm only depends on the position of the end effector.
Oh, yeah.
So you can eliminate everything in your CCD algorithm except for that final frame G calculation.
But if we're plotting it the same way we saw the plot.
Right. So that's where I went through and created a function for my plotting, because then after I determine the set of parameters that get us to that point, then I can just send them to my plot utility and it draws the manipulator, so. Cool. Any questions?
So this is due on
Thursday of next week.
Thursday of next week, and we
Yes.
have the little writing assignment. Is
Yes,
due-
and I went through, okay, so let me pull that up real quick. I suppose I can leave that on the screen. So, have you guys watched anything else that Jonathan Frakes narrates? He doesn't necessarily always strike me as the most credible guy, but, I mean, what can you say? He was on Star Trek for a long time. So anyhow, he narrates the second one, the robots and military applications thing. And it's really kind of funny because when he has an expert that, you know, is discussing their research or whatever else, he has this little frame like, you know, my name is so-and-so and I am the director, you know, so it's kind of like a sensationalized, not Nancy Grace sensationalized, just, you know. Anyhow, so, there we go. The programs all look good. Essentially, I just wanted to make sure that everyone did in fact work. If you didn't get the entire thing working, just do your best to get it working for me and get it turned in as soon as possible. So assignment list. And then, so what you're going to do is you're going to choose one of the two videos to watch. And after you do, you're going to go through and provide a response describing one of the robots that's introduced in the video. There's quite a few that are introduced in both. In fact, there's some overlap between the two videos, so that's kind of cool. But you're going to choose one of the robots that they introduce and discuss whether or not it satisfies, you know, the definition of what a robot is supposed to be as we've introduced it in class. Okay, so namely, it's supposed to be programmable and reconfigurable. Okay, well, guess what? If we have a military robot or military robot, what can we say about the reconfigurability of that robot or the reprogrammability of that robot? It's probably designed for a specific task, and therefore they call it a robot to sell it to the generals and stuff. But is it really a robot by definition? No, probably not, right? I mean, there are some instances where DARPA is developing true robots, but a number of the, you know, devices that they call a robot simply aren't. So does that kind of make sense? So that should be pretty straightforward. Let me show you the little bit here.
Ministry of Defence. And there is huge controversy about this, suggesting that a swords combat robot had swiveled its guns towards friendly troops, prompting it to be withdrawn from Iraq. I'm Nick Pope. I worked for 21 years at the British Ministry of Defence.
So he has like
and there is
every
huge
person
controversy
you've
about
interviewed
this. There are different stories
has
being
to
bandied
do that,
around,
you know.
all sorts of
So,
rumours and
what's going on,
denials.
and what do you do, and how important of a person are you, so, yeah, so. The second video, like I said, is, you know, designed for people that, you know, want to watch that stuff, but the first of the two videos is definitely the better of the two videos, so.